This video is going to discuss Kepler's laws of planetary motion. The objective is that students will be able to recite the equations and principles of Kepler's laws of orbital motion. So make sure you have, wherever you're taking your notes, and something to write with. And let's get started. A little bit about Johannes Kepler. He was born in 1571 and lived till 1630. He was a German astronomer, and he used years of astronomical observations from his predecessor, who is named Tycho Brahe, to come up with 3 laws of motion that describe all the motion of all the planets. His first law of orbital motion, or planetary motion, was that the path of every planet around the Sun is an ellipse with the Sun at one focus. I'm going to explain what the focus part means in a second, and what an ellipse is. An ellipse is an elongated circle with a geometric shape. Instead of having a central point like a circle, like if you use a compass and make a circle, it has one center point. An ellipse has 2 central points called foci. And foci is the plural form of focus. So if it has more than one focus, it has foci. It's the plural. So I'll show a picture of this on the next slide so it makes a little bit more sense. So here, if the Sun is at this focus, there's another focus over here somewhere. It's like just an empty point in space. But the planet sweeps out kind of this oval shape, it's called an ellipse, around the Sun. Notice the Sun is not at the center of that ellipse. It's on one of the foci, one of the 2 focus points. A little bit different. And there's 2 words in here, perihelion on the right and aphelion on the left. And as shown in the drawing, a planet's perihelion point occurs when it's closest to the Sun. So over here, if this planet that the pencil's drawing comes all the way over here, whenever a planet is at its closest point to the Sun in its orbit, that's called perihelion. The opposite of that, when the planet is as far away from the Sun as it'll ever be, that's called aphelion. That would be over here to the left. If both of the focus points, or foci, are located at the same point in the center, then the shape of that ellipse would actually become a circle. So a circle is a very special type of ellipse where both of the foci are at the same point. Kepler's second law of motion says that each planet moves so that an imaginary line drawn from the Sun to that planet sweeps out equal areas in equal periods of time. What that really means is that when a planet reaches perihelion, when it's closest to the Sun, it's moving faster than when it reaches aphelion. Since it's closer, it's going to be moving faster. And here's a picture that kind of sums it up a little bit better. So if you imagine the Earth is going around the Sun, and the Sun's at one focus, so it's not at the center of the orbit, but it's off center a little bit on one of these focus points. Then at perihelion over here, which is called area 1, that area that it sweeps out, like if you think of this shape here, that area is the same as area 2. Like if you were to calculate the area of that shape, these areas are the same. Area 1 equals area 2. In 30 days, over here on the left, since it's moving faster, it's going to go a farther distance here in this 30 days on the left than over here. Here, since it's further away, it's moving more slowly. It doesn't cover as much distance along the ellipse as in over here on the left. But either way, it still sweeps out the same amount of area in the same amount of time. Kepler's third law says that the ratio of the squares of the periods of any 2 planets revolving around the Sun is equal to the ratio of the cubes of their mean distances from the Sun. Whew. This means basically that the further a planet is from the Sun, the longer it's going to take to revolve around the Sun, if I had to simplify that. Therefore, Mercury, which is the closest planet to the Sun, revolves the fastest of all the planets in the solar system. So a little bit more on the third law. Isaac Newton came along and corrected it and made it even better. And he established that for any one planet, you can have a mathematical relationship to find the period of the planet, or the time it takes to complete one revolution. So this equation became T equals 2 pi over the root of capital G times the mass of the Sun, to blah, blah, blah. These equations look kind of crazy. Either way, both these equations say the same thing. It's just whether you square t and have it look a little bit nicer over here without a weird 3/2 power and no square root sign in the bottom, or if you just leave it as t without the square, then everything else has to be square rooted, basically. So t is the period of the planet measured in seconds, and if you don't remember, period is the time it takes to complete one revolution. So the period of Earth is 1 year. Capital G is still the universal gravitational constant, just like in Newton's law of universal gravitation, and it's still 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Capital M is the mass of the host. For planets, that's the sun. So capital M for any planet in our solar system is going to be the mass of the sun, which is a huge number, 1.99 times 10 to the 30th kilograms. But this equation could also work to figure out the period of the moon, where the Earth would be the host. So you'd use the mass of the Earth to figure out the period of the moon. And R is the average distance between the planet and the sun, or the thing orbiting and its host, or whatever. Any two objects orbiting each other. So R would be the distance between them. And it's measured in meters like distances usually are. And that wraps it up for Kepler's 3 laws of planetary motion. Remember to take the EdModo quiz and bring your notes to next class. Thanks for watching.